Hello, and I just wanted to spend a little bit of time talking to you about the covalent molecules. I'm not sure that we talked about those enough, and make sure that you're aware of their properties. And the first one is that the shape of these molecules is super important. So if you take a look at the two molecules we have here, C10H24N2O2, you can see that depending upon their shape, they're two totally different molecules. And so the shape of these covalent molecules is very important. S-meth is an illegal drug, and R-meth is Vicks inhaler. So big differences here. There are 5 shapes you need to know. And here they are: linear. The molecules are in a straight line. Now, I like to think of it as the molecules. The technical way to think of it is electron density. And that's really what these shapes are based out of. The next shape is bent. You can see we've got like about it looks like to me a 90-degree angle. It's not. It's really about 109 or 120. You do not need to know the angles. The next one is the next two are sort of triangular shaped molecules, hence their name trigonal. The first one is flat. So these 3 molecules are flat and would lay flat in your hand. The other trigonal molecule, the trigonal pyramidal, is poofed up in the middle a little bit, like the pyramids in Egypt. Hence the name trigonal pyramidal. And the last shape that you need to know is tetrahedral. So there are 4 molecules attached to the central atom. And the shape of these molecules is determined by what's attached to the central atom. So you're going to need to look at the central atom and figure out what's attached there. There can be 2 things attached: other atoms, and then lone pairs of electrons. Electrons that are there that were not used in a covalent bond. Everything wants its own space. And so that's part of the problem with figuring out where these or the shapes of these molecules is what is taking up space. And actually lone pairs take up more space than other atoms. And so this is a little chart that I often use. You may want to snap a picture of it to figure out what shape the molecule is. So if there are 3 atoms attached to a central atom and no lone pairs, that molecule would be trigonal planar. And so here's some examples for you so that you can see the central atom, the lone pairs, and other atoms. So here's our central atom in each case. And you can see in the case of this CH4, there are no lone pairs. Just 4 other atoms attached to the central atom. Hence its hence its tetrahedral shape. In this one over here, this NH3, there is a lone pair attached to the central atom. That lone pair then pushes the other atoms down, kind of out of the way, and making it kind of poof up and giving it a trigonal pyramidal shape. The other one, H2O, because there are 2 atoms attached to the central atom and 2 lone pairs, it makes it a bent shape. So you will need to be able to look at these molecules and figure out their shape. And this is just like a little diagram so you can see how the space of shared electrons is in the picture at the top. And then if there's lone pairs, how much more space they take up. And you can kind of take a look at the bonds. If there's single bonds and double bonds, that will also kind of affect the shape a little bit. But like I said, you're not responsible to know bond angles. Now, another factor that we kind of take a look at when we're taking a look at shape is electronegativity. And you already know the trend of electronegativity. You know what it is. Here's a picture of it. An atom's ability to attract electrons toward itself, not take them, just attract them in a bond. And this is one of my little charts I like to use. This is one I would have a picture of if I were you. And so if you're looking at the molecule and you're seeing how are they sharing their electrons, that's really what electronegativity is about. How do they share their electrons? Are they sharing them evenly? If so, they would have a very similar electronegativity, like 0 to 0.5. If they're not sharing them evenly, they would have an electronegativity around 0.5 to 2.1. and not be sharing them evenly, and we would call that a polar bond. And so always having a table of electronegativity handy will be very helpful. I will give you a table of electronegativity for your next test. All right, so let's go ahead and get started practicing. I would suggest you take out paper, pencil, have a table of electronegativity handy, and see if you can go ahead and draw a molecule of carbon disulfide. Figure out its electronegativity and its shape. All right, so how did you do? Well, the first thing I have to do is I've got to write the formula for carbon disulfide, because I got to kind of translate these words into a formula. So CS2. Then I got to think about valence electrons. That's what I always do next. And so I know carbon has 4 valence electrons. Each sulfur has 6 valence electrons, giving me a total of 12. So I've got a total of, in this molecule, 16 valence electrons I need to account for. Next, I'm going to figure out my central atom. And I'm going to figure carbon as my central atom because it came first and there's the fewest of them. And that's generally what we do. And then I'm going to put my S's in there. And I already put my bonds in. You can see my bonds right there. And so that is, each of those bonds is 2 electrons. So I just accounted for 4 valence electrons. So that means I have 12 more to put around. And generally the rule with putting them around is that we're going to put these other 12 valence electrons, these lone pairs, on surrounding atoms, not the central atom. And then we're going to check to see if everybody has an octet. Does everybody have an octet? And so we're going to have each atom kind of look around itself and see if it has an octet. And so as I look at this sulfur does think it has an octet because of those shared electrons, but carbon does not feel like it has an octet. It only feels like it has 4 valence electrons. And so what we're going to have to do in this situation is we are going to take 2 of these electrons, we're going to take them out of here, and we're going to make them a double bond. And that's typically what we do when we're doing that. And that's how you figure out if you need a double bond. And now, let me look. Does everybody have an octet? Yes, and all my electrons are accounted for. And now I can kind of take a look at the electronegativity and the shape of this molecule. Obviously, our shape is linear. We have 2 atoms attached to our central atom and no lone pairs. And I can see, obviously, it's in a straight line. And now I'm going to take a look at my electronegativity. Oh, wow. Carbon and sulfur both have the same electronegativity. That means they're going to be sharing these electrons evenly. So there is going to be no difference in sharing. So that means this molecule has to be nonpolar. So hopefully you were thinking that as well. Let's take a look at another example. Hydrogen monofluoride. All right, great time to stop, try to draw this molecule, figure out its shape, figure out its electronegativity, and then check how you did. All right, so again, first thing I have to do is translate this into formula, monofluoride. So that's going to be 1 hydrogen, 1 fluoride. And I've got 1 valence electron. Whoops. Come on, go back. 1 valence electron with hydrogen and 7 with fluorine. So that's a total of 8 valence electrons. I know hydrogen only needs 2, so let me go ahead and draw that molecule. Put in my 2 shared electrons. So now I have 6 more to put around. So let's see. Well, hydrogen is good. Hydrogen is our exception of always. It doesn't need a whole octet. It only needs 2. And so there we go. Our molecule of hydrogen fluoride. All right, so what's its shape? Well, we only have 2 atoms attached to each other, no central atom, so it is linear. Let's take a look at our electronegativity. So how are these electrons being shared? Well, so it looks like they're shared between the 2, but in fact, fluorine is way more electronegative. So it looks like they're being shared right there, but actually they're being pulled more towards fluorine, making this fluorine end of this molecule a little bit negative, leaving this hydrogen end of this molecule a little bit positive. And so this linear molecule then we do have a polar bond here, and because of the shape of the molecule and the difference in electronegativity, we also have a polar molecule. Hopefully you were thinking that as well. So let's go ahead and take a look at our next one. I believe this is also one that you have for this oxygen dichloride. This one may be on active chem homework. All right, so again, take a look. Things that you have to figure out. Draw the molecule. What's it look like? What's its shape? What's its electronegativity difference? And is it polar or not polar? So once again, I'm going to translate this into, so oxygen, dichloride. So that's OCl2. We have 6 plus 14 valence electrons. So that's 20 valence electrons. I'm going to put oxygen in the center. Nature likes symmetry. So I'm going to put a Cl on each side. Now, as I've put in those bonds, that's 4 valence electrons. So we have 16 left to put around. And once again, I'm going to put them on the surrounding atoms, 2, 4, 6, 8, 10, 12. Okay, so now I have 4 left. So I'm going to go ahead and put those on the central atom because I do have them left over. I don't need to make any double bonds. Let's check to see if everybody has an octet. So it looks like this chlorine does, oxygen does, the other chlorine does. All right, so what's the shape of this molecule? Hopefully, hopefully you were thinking it is bent because we have 2 lone pairs of electrons attached to that central atom. So as you're kind of drawing that, you got to kind of take a look at that as well. And so let's go ahead and take a look at our electronegativity difference. So our electronegativity Now, even though we have 2 chlorines here, we're just taking a look at this bond and where the electron's being pulled. And with an electronegativity difference of 0.5, this is going to be a non-polar molecule. So we have a non-polar bond and a non-polar molecule. So I hope this helps you as you're reviewing, as you're doing the active chem. There are several molecules where you're going to have to draw them, figure out if they're single bonds, double bonds. If you have any questions, please feel free to reach out and let me know. Have a great day.